We have talked about the polar amplification or Arctic amplification. A new paper that has now come out just last week provides a scarier picture, saying that in fact the polar amplification has been underestimated and models are not doing it so well either. So there is a context to this. If we look at this a figure from NOAA, you can see that clearly there is polar amplification, and we have always talked about how critical it is to understand how the East Pacific is doing as opposed to the West Pacific, because of the ocean's ability to take up heat here and the feedback in terms of the sea surface temperature gradient and the winds and continued cool temperatures over here, or less warming than the West, and so on. But coming back to the Arctic amplification, this also highlights the problem with data here. There's not always good coverage here, but we are very sure that there is polar amplification happening, and we are quite sure about the processes involved, not just ice albedo feedback, but remember our old friend Clausius Clapeyron. As warming happens, humidity goes up, water vapor, which is a strong greenhouse gas, clouds are formed, and clouds can be positive or negative feedback depending on whether they are high thin clouds or low thick clouds. So here there is amplification from those cloud water vapor feedback processes as well. This new paper looks at the annual mean temperature evolution in the Arctic, and it shows various data products. So this is another thing we've talked about, that people used raw data available from various sources and do reconstructions in space and time, especially when you go back in time here. You can see that they agree better, for example, over the satellite period than over the period where they're grabbing data from various other sources and doing their own method of filling the holes in space and time. And there is one product which is showing here. So if you look at annual mean temperature anomalies in the Arctic, defined as this latitude band, in dark colors and globally, so light colors, during 1950 to 2021, derived from various observational data set. Temperature anomalies have been calculated relative to the standard 30-year period of 1981 to 2010. It doesn't matter, baseline just shifts the relative sizes, but the message is still the same. Shown are also the linear temperature trends for 1979 to 2021. So you can see that these are the trends here. Annual mean temperature trends for the period 1979 to 2021 derived from the average of observational data sets. That's this one. Areas without statistically significant changes are masked out, so you can see some white regions over there. And this is the local amplification ratio calculated for the period 1979 to 2021, derived from the average observational data set. The dashed line in B and C depicts the Arctic Circle here. So one should note the differences, but also the fact that amplification factor can be estimated, which is the Arctic warming versus the rest of the world. And this is critical because it also has lots of cascading effects, being the Arctic sea ice loss, meandering of the jet stream, heat waves, even the monsoon gets affected, and so on and so forth. So the estimated Arctic amplification ratio and its 5th and 95th percentiles, calculated for the period 1979 to 2021 from the observational data sets, CMIP5 ensemble and CMIP6 ensemble. CMIP5 and 6 are of course the coupled model intercomparison projects run by IPCC, WCRP, which are used for the assessment reports. This one came out in 2014, this came out in 21-22, and there are some improvements, but this is always a struggle to say how much improvements are being accomplished. So here again the Arctic is defined this way, but you can see that the various data sets and CMIP and CMIP5 and CMIP6 show that Arctic amplification is grossly underestimated by the models, and the 5th and 95th percentile confidence limits also show great differences between models and observations. So without saying in detail why the estimates are much higher than before and why models are not doing it so well, in general, models don't do low frequency variability well as well. So there is a multi-decadal variabilities, Atlantic multi-decadal oscillation, Pacific decadal oscillation, North Atlantic oscillation, and so on and so forth. So models are amazing. Given the energy at the top of the atmosphere, they can do everything, but they are not perfect, so we have to be aware of their biases. It's also important to note that there is seasonality in the amplification. So if we look at the Arctic amplification over a year and the annual mean, again observational estimates versus models, seasonality of the 43-year Arctic amplification ratio, the red circles indicate observed Arctic amplification as derived from the average of 4 observational data sets. The orange lines indicate medians of CMIP6 realizations, and boxes show first and third quartiles. Whiskers extend 5th to 95th percentiles of the realizations. Numbers in the upper row give percent rank of observed Arctic amplification in CMIP6 ensemble. Why did I stress CMIP? CMIP6 ensemble distributions. The Arctic again is defined north of 66.5. So you can see that there are not only differences between the observations and models, but there are also seasonality differences, which matters because where the sea ice tends to melt and can have bigger impact into the winter. So if winter amplification is larger and you are coming out of a low sea ice extent, then you're going to lose more of it, which can explain the continued downward trend in the Arctic ice, for example. Again, strong winds, sorry about that. I have no idea how to stop it beyond this at this point. I have to close the screens as well, but I will suffocate in that case. So there is another way to look at the Arctic amplification between the difference between observations and models. The probability of observed Arctic amplification in the climate model ensemble. So you look at the density, probability density functions and the range or frequencies of Arctic amplification in models. So CMIP5, CMIP6, and then MPI Max Planck model, and this is one Earth system model from China, I think. Doesn't matter. So you can see that CMIP5 was way off. CMIP6, is it better? Well, maybe marginally better compared to, so red line is the observation. It denotes the 43-year Arctic amplification ratio. There is reasons to compare different models. So this model seems to do better compared to CMIP5 and CMIP6, but oftentimes something that is done well here doesn't necessarily mean it is doing better than these models everywhere else. If you look at monsoon historical variations and trends, or El Nino behavior and so on, this model may be worse than others. So it's a tricky business when you have a full coupled system with all kinds of internal feedbacks between vegetation, carbon cycle, ocean warming, glacier melt. Many models may not even have land ice, sea ice feedbacks, etc. You cannot just conclude anything based on better performance in Arctic amplification, but one can look for dynamic consistencies within the models. If this is doing Arctic amplification that is has a larger bias with respect to the observations, and this has less, does this translate to dynamically cascading impacts on high latitudes to low latitudes, and variations at different frequencies, and so on and so forth. But nonetheless, the main message is that the Arctic, by these estimates revised based on various approaches, seems to indicate that Arctic amplification is actually quite large and models are not doing so well. What does this mean? Arctic still remains an indicator, a poster child, a litmus test for global warming impacts, and if by 2030 we are seriously on the way to losing all of the Arctic ice, or if it has already gone by then we have to worry also about the geopolitics of it in terms of fighting for the energy that's already started, because remember, Arctic was very warm during the time of the dinosaurs. A lot of photosynthesis, oil and gas at the bottom. A lot of countries are vying for it, and of course also the impacts of Arctic warming on the rest of the planet in terms of climate has to be looked at as well. Okay, of course it's possible that Arctic warming will benefit some countries like Russia, produce a lot of wheat in Siberian region with warm temperatures and so on, but right now we just have to worry about the Arctic warming so much faster and the Arctic amplification being so much larger than we had thought before. Okay.